Enter the boldest hypothesis in modern planetary science. Planet 9 might be exerting its gravitational will hundreds of times farther away than Earth's journey around the Sun. If such a planet exists, it could be 5 or even 10 times the mass of our own world. Picture a world so distant that sunlight is a mere glimmer, so cold that its atmosphere could collapse into ice, so remote that no human-built spacecraft has ever come close. Yet, as astronomers mapped these orbits, a disturbing pattern emerged. These scattered worlds, separated by vast gulfs of emptiness, were not moving at random. Instead, their orbits seemed eerily aligned, as if a hidden hand was guiding them, a force strong enough to shepherd entire populations of ice-bound wanderers. This alignment was not just a minor quirk. It was statistically improbable, a cosmic coincidence that begged for an explanation. Journey with us to a place where sunlight is barely more than a distant memory, where the solar wind's breath is faint, and where time itself seems to slow. Here, far beyond Neptune's ghostly blue orbit, clusters of icy bodies, fragments of ancient collisions, leftovers from the solar system's tumultuous youth, drift in fragile harmony. Each of these objects, called trans-Neptunian objects or TNOs, traces a path so distant and slow that a single trip around the Sun can take thousands or even tens of thousands of years. What if everything you thought you knew about our solar system was only half the story? Imagine if, hidden in the cold and silent reaches beyond the known planets, there was a colossal secret, one so significant it could upend our very understanding of how solar systems form, evolve, and survive. For centuries, humanity has gazed upward, mapping the familiar planets, cataloging their motions, and believing that our star's retinue was complete. But perhaps, just out of sight, the solar system is harboring a giant, an undiscovered world whose gravity is steering cosmic traffic from the darkness, leaving only subtle clues for those who know where to look. And yet, for all this effort, no telescope has captured a direct image. No signal, no shadow, no streak in the darkness has resolved into the unmistakable evidence of a new planet. Instead, what astronomers have found is a deepening mystery, a pattern of orbits growing ever more peculiar, as if nature were scattering breadcrumbs for us to follow, only to lead us deeper into the unknown. For nearly a decade, this possibility has consumed the astronomical community. The search for Planet 9 has not been confined to a handful of experts. It has galvanized data analysts, inspired backyard stargazers, and drawn in some of the world's most powerful telescopes, from the Subaru telescope atop Mauna Kea to the Dark Energy Survey's mighty camera in Chile. Supercomputers have been pressed into service, running endless simulations of the outer solar system's ballet. Could Planet 9 truly be out there? Its presence betrayed only by the subtle dance of icy bodies on the edge of darkness? Or has the scientific world been seduced by a mirage, a trick of statistics, a phantom conjured by the very methods we rely on to interpret the cosmos? The stakes could not be higher. If Planet 9 is real but remains hidden, then our understanding of the solar system's evolution is incomplete. If it is a fantasy, then years of research and billions of dollars in funding may have been spent chasing a ghost. To unravel this enigma, we must journey back to where it all began, not with a sighting, but with a puzzle so quiet, so subtle, that it might have been missed entirely. Our story begins in the year 2016, when astronomers Mike Brown and Konstantin Batygin noticed that a handful of icy worlds beyond Neptune, objects with names like Sedna, 2012 VP113, and 2010 GB174, were not scattered randomly as expected. Instead, these extreme trans-Neptunian objects, or ETNOs, shared a curious alignment. Their orbits pointed in roughly the same direction, and their tilts were strikingly similar. History is rich with stories of scientific breakthroughs that began with unexplained anomalies. In the 19th century, astronomers noticed that Uranus's orbit was slightly off from predictions.
After years of calculations, they pinpointed Neptune before it was ever seen, a triumph of mathematics over mystery. Could Planet 9 be the 21st century's Neptune? Or would it become another Vulcan, a hypothetical world once believed to explain Mercury's wayward orbit, only to be banished by Einstein's theory of relativity?
Brown and Badigan's proposal electrified the scientific community. Observatories across the globe began scrutinizing the sky. Data miners scoured old photographic plates and digital archives, hoping for a missed blip or forgotten anomaly. Citizen science projects like Zooniverse invited the public to help search for moving objects in decades of sky images. The world was united in pursuit of a cosmic ghost. For Brown and Badigan, this was more than coincidence. They turned to mathematics, modeling the gravitational interactions of known planets and these distant objects. The numbers told a compelling story. Only a massive, unseen world could be gently steering these orbits into such a neat cluster. Their calculations suggested a planet at least 5 to 10 times as heavy as Earth, orbiting between 400 and 800 times farther from the Sun than our own world. For perspective, Neptune is about 30 times farther from the Sun than Earth. This mysterious planet, if real, would be so distant that sunlight would take hours to reach it, and its year would stretch well beyond human lifetimes.
And yet, the search for the unseen is fraught with peril. If the evidence was misleading, years of work, millions of dollars, and the reputation of planetary science itself could be at stake. While excitement rippled through astronomy, a wave of skepticism swelled. Was this pattern real, or an artifact of small number statistics and human bias? Could we be seeing faces in the cosmic clouds, inventing order where none exists? Science advances by testing its boldest claims. The search for Planet 9 has become one of the most extraordinary and contentious quests in modern astronomy. Nearly a decade later, the mystery remains unsolved, with the evidence growing both more seductive and more ambiguous.
Let us examine the case for Planet 9 with a critical eye. For years, astronomers have used supercomputer simulations to show that adding a hidden, massive planet to our solar system can neatly explain the strange clustering of far-off icy objects. When a planet of the right mass and orbit is included, the observed ETNOs snap into alignment with the simulations, just as we see in real life. It is, at first glance, a compelling confirmation.
But skepticism lingers. The case hinges on fewer than 24 objects, a tiny sample by astronomical standards. Most have been found by only a handful of surveys, often peering in similar directions and using similar search methods. Imagine searching for rare animals in a single part of a vast forest. If you always look in the same grove, your discoveries will cluster, even if the animals are evenly spread elsewhere. Could astronomers be mistaking a search bias for a cosmic conspiracy?
Despite years spent scanning the sky with the world's most powerful telescopes, Subaru, Vista, Pan-STARRS, and more, no one has glimpsed Planet 9 directly. Each new survey brings hope, only to end in silence. This absence has split the astronomical community. Some treat every newly discovered ETNO as further evidence for Planet 9, while others see each exception as a nail in the theory's coffin. Yet, just as hope seemed to dim, the past offered a new lead. Sometimes, the keys to the future are hidden in the overlooked archives of yesterday. The doubts do not end there. Some researchers propose that other forces, a vast disk of unseen debris perhaps, or the lingering gravitational tug of a passing star millions of years ago, could mimic the fingerprints of Planet 9. Elsewhere, theorists have even suggested that the answer might not be a planet at all, but a subtle tweak to the laws of gravity themselves. Modified Newtonian dynamics, or MOND, has been invoked to explain galactic mysteries before. Could it account for our solar system's anomalies as well? With every enigmatic discovery, every icy wanderer whose orbit defies expectations, the stakes climb higher. If Planet 9 is an illusion, the fallout could be severe.
Research careers, funding for deep space missions, and the credibility of planetary science itself could all be threatened. It would not be the first time. In the early 20th century, astronomers spent decades searching for Planet X, hoping to explain wobbles in Neptune and Uranus's orbits. Eventually, it was revealed that data errors, not hidden planets, were to blame. Could history be repeating itself? Desperate for answers, astronomers delved into decades of forgotten sky surveys, especially those taken in infrared light. These surveys, such as the infrared astronomical satellite mission from the early 1980s and the more recent Wide-Field Infrared Survey Explorer, had mapped the heavens for faint, slow-moving objects. The hope was that a hidden clue, a faint streak or moving dot, might have gone unnoticed. In 2017, another twist arrived. Astronomers discovered an object designated 2017 OF-201, whose orbit was even more extreme, stretched far from the sun and tilted at a wild angle. But instead of joining the supposed cluster of Planet 9's influence, this object traveled alone, hinting at a far more chaotic and unpredictable frontier. Then, a breakthrough. Scientists spotted a distant object with an utterly bizarre tilt, moving slowly against the background stars. For a moment, excitement surged. Could this finally be the elusive Planet 9? Yet, as they tracked its motion and measured its faint glow, the evidence fell short. This object, while strange, did not match the predictions for mass, brightness, or orbital path. It was a thrilling find, but it was not the missing planet. Rather than clarifying the picture, each new discovery seemed to add complexity. Every anomaly, every exception, forced astronomers to re-examine their assumptions. Was there truly a hidden giant shaping these orbits, or were we simply witnessing the unpredictable dance of cosmic chaos?
The quest, once imagined as a straight path to revelation, now seemed a labyrinth. Each new observation tangled the puzzle further. The answer could force us to rewrite the story of our solar system's birth, or expose a flaw in how we interpret the cosmos.
But if Planet 9 is out there, a world 5 or more times the mass of Earth, orbiting hundreds of times farther than our own planet, how did it get there? To answer this, astronomers had to challenge everything they thought they knew about planet formation and migration. The debate became fiercer. Some researchers raised the uncomfortable idea that the apparent clustering of Etanos was an illusion born from the way telescopes scan the sky. If most surveys target certain regions, then the objects we find will naturally appear grouped, even if there is no real gravitational shepherd. Could the entire hypothesis be an artifact of our own methods? There are two leading theories. The first suggests that Planet 9 formed close to the Sun amid the swirling disk of gas and dust that gave birth to Jupiter, Saturn, Uranus, and Neptune. In the solar system's violent youth, gravitational clashes between giant planets could have hurled this world outward, exiling it to the solar system's frozen fringe. This process is not mere speculation. Computer simulations show that giant planets can and do scatter each other in the early chaos of planetary systems. In fact, the discovery of so-called hot Jupiters, gas giants orbiting close to distant stars, demonstrates that planetary migration is a common fate. The second theory is even stranger. Perhaps Planet 9 did not begin in our solar system at all. Instead, in the crowded nursery of stars where the Sun was born, another star might have shed a planet, an orphan world, wandering alone. In a cosmic near-miss, the Sun could have captured this planet, adopting it as its own. Such captures are rare, but not impossible. In recent years, astronomers have found evidence that stars can exchange planets in their youth, especially when they drift close in stellar clusters. Yet, these remain only theories. The universe does not surrender its secrets lightly. To answer the riddle, astronomers need direct proof. A new era of discovery is about to begin with the imminent arrival of the Vera C. Rubin Observatory in Chile. Once operational, the Rubin Observatory will scan the southern sky with unprecedented depth and regularity, creating a motion picture of the heavens. Its powerful camera, the largest ever built for astronomy, will capture faint, slow-moving objects, precisely the kind of world Planet 9 is predicted to be. Both scenarios are supported by sophisticated computer models. Simulations show that a planet 5 to 10 times Earth's mass could be flung to the edge and survive for billions of years, or be captured and settle into a stable, distant orbit. Historical parallels abound. In the early solar system, Jupiter is thought to have migrated inward and outward, scattering asteroids and shaping the architecture we see today. Similarly, Neptune's migration is believed to have sent comets streaming into the inner solar system, creating the late heavy bombardment. Could Planet 9 simply be another chapter in the solar system's epic of migration and chaos? The hunt for Planet 9 is more than a scientific mystery. It is a test of human curiosity, endurance, and humility, a confrontation with the unknown that refuses to yield easily. If Planet 9 is out there, the Rubin Observatory's relentless survey may at last reveal it. This would not be the first time a leap in technology opened new cosmic windows. In the late 20th century, the Hubble Space Telescope revolutionized our view of the universe, revealing galaxies and nebulae never before seen. The Rubin Observatory could do the same for the solar system's dark outskirts. But the search does not rest on one instrument alone. Across the globe, citizen scientists pore over public data, hunting for overlooked clues. Space telescopes like the James Webb are capable, in theory, of detecting the faint heat signature of a distant planet. Algorithms driven by artificial intelligence process millions of images, searching for the tiniest hint that something has been missed. This worldwide effort, uniting professionals and amateurs, supercomputers and human curiosity, is a testament to the enduring spirit of discovery. The stakes are immense. Billions of dollars in technology, years of human labor, and the credibility of planetary science all ride on the outcome. If Planet 9 is found, textbooks will have to be rewritten. Our understanding of planetary formation, orbital dynamics, and even the definition of what constitutes a planet will be changed. If the search comes up empty, scientists will be forced to explain the strange orbits without recourse to a hidden planet, perhaps revisiting fundamental theories or admitting that the universe sometimes defies our neatest models. Meanwhile, funding agencies and scientific committees must weigh the value of continued searches. With every year that passes without a detection, pressure mounts to justify the investment. Yet, the same tension drives innovation. New instruments, new methods, and new collaborations are born from the challenge. To bring this closer to home, consider how similar debates have played out in the past. In the late 19th century, the planet Vulcan was hypothesized to explain Mercury's orbit. For decades, astronomers searched in vain, until Einstein's theory of general relativity revealed that Mercury's motion could be explained without a hidden planet. The null result did not spell defeat. It paved the way for a new era in physics. In the late 20th century, astronomers searching for Planet X to explain supposed irregularities in Neptune and Uranus's orbits eventually discovered Pluto, but it was too small to have the required influence. The real solution lay in correcting earlier observations. The broader implications are profound. If Planet 9 is found, it would join the ranks of the solar system's major planets, a new world to be explored by future spacecraft. It might hold clues to the formation and migration of giant planets across the galaxy, informing our understanding of exoplanet systems. It could even harbor its own moonlets, rings, or a system of icy satellites, each a world unto itself. Practical steps for the search are manifold. First, astronomers catalog every new TNO, measuring its orbit with painstaking precision. They feed these data into simulations, testing whether different masses, distances, and orbital inclinations for Planet 9 could reproduce the observed patterns. Telescope time is allocated to scan likely regions of the sky, often near the galactic plane, where stars are densely packed and small, faint objects are hard to spot. Machine learning algorithms sift through petabytes of image data, flagging anything that moves against the background stars. When possible, observers compare discoveries with archived data, seeking to extend the orbital arcs and improve predictions. But if Planet 9 proves to be a mirage, the lesson would be no less valuable. Science progresses not only through discoveries, but also through the discipline to accept null results. The story of the search would become a case study in skepticism, statistical caution, and the power and peril of computer simulations. As the search presses on, the story of Planet 9 endures as a testament to humanity's quest for knowledge. Whether the final answer is revelation or disappointment, the journey itself enriches our understanding, sharpens our tools, and inspires future generations to look deeper, ask bolder questions, and never settle for easy answers. But before any verdict is delivered, one question lingers in every astronomer's mind. What if Planet 9 is not the answer at all? What if the strange orbits and distant motions are neither the handiwork of a hidden world nor the result of flawed statistics, but instead a sign of new physics waiting to be discovered? Throughout history, the greatest advances, heliocentrism, relativity, quantum mechanics, have arrived when the universe refused to fit our expectations.
In science, true closure is rare. Sometimes it is a single discovery away. Sometimes it forever recedes beyond the horizon of what we can know. After nearly 10 years of searching, the hunt for Planet 9 stands at a pivotal moment. If this hidden world is real, it will not simply be another planet added to our maps. Its presence would force us to rewrite the story of our solar system's birth, rethink how planets migrate, and reconsider what makes a planet a planet. If, on the other hand, Planet 9 is nothing more than a cosmic mirage, if the evidence dissolves under scrutiny, then the lesson is equally profound. We will relearn that the universe is not built to satisfy our expectations, and that even the most seductive theories can be undone by the weight of careful data. The stakes are high, and the outcome remains unknown. Textbooks may have to be rewritten, or the search may end in humility. But regardless of what the data ultimately reveal, science will emerge stronger, its methods tested, its curiosity undimmed. As the search for Planet 9 continues, we are reminded that the cosmos still holds secrets. Our greatest advances begin not with answers, but with the courage to ask the impossible questions. Whether the final chapter brings confirmation, refutation, or a new mystery altogether, the story of Planet 9 will continue to inspire those who dare to look beyond the edge of the known and into the vast, uncharted darkness.